Today we are going to discuss about viscous flows. Due to relative velocity between two layers, the velocity gradient exists. Right here, this is one solid boundary. One solid boundary. This is perpendicular to solid boundary. This is y direction. This is x direction. Over the solid boundary, the velocity is 0. The velocity gradually increases. Here, this is the free stream velocity capital U. At one location, the velocity, this is one velocity, this is another velocity, this is the velocity, gradually velocity increases. So at one location, the velocity reaches to the free stream velocity. This is known as boundary layer thickness. This is already explained. This is known as thickness of the boundary layer. Now, due to relative velocity, that means this is one velocity, this is one velocity. This is the velocity at this layer. This is one layer, this is the another layer. The velocity over this layer is u. The velocity over this layer is u plus du. Say this is du velocity, right? This is one layer, velocity u. This is the another layer. This velocity is u. This velocity is du, right? And a distance between these two layers is dy. Okay, because of the velocity is 0 over the plate, gradually increases because of the change of velocity having the velocity gradient. Now change in velocity is equal to what is the velocity? Right, change in velocity du is equal to u plus du minus u, that is the velocity over this layer, u velocity over this layer, u plus du, u minus u cancel, this is equal to du. Change in velocity is equal to du at a depth of dy. Therefore du by dy exists here. Okay, due to relative velocity between two layers, so the velocity gradient exists, so and hence shear stress is developed. That is, shear stress is equal to mu into du by dy. Right? This is about. But in this case, in case of viscous flows, flow of viscous fluid through the pipe, velocity distribution across the section, and flow of viscous fluid between two parallel plates, velocity distribution across the section. These two heads we are going to discuss here, right? Flow of viscous fluids through the circular pipe. We are going to discuss these points. One, shear stress distribution across the section, velocity distribution across the section, ratio of maximum velocity to average velocity, and last one, drop of pressure for a given length L of the pipe. These 4 points we are going to discuss if the viscous fluid is flowing through the pipe. Right. First one, flow of viscous fluid through a circular pipe. Viscous fluids means if the Reynolds number is 2000, the flow is laminar flow or viscous flow, right? If the Reynolds number is less than 2000, the flow through the circular pipe will be viscous and laminar, right? This is clear. Now the expression for the Reynolds number Re equal to rho v d by mu, where rho is Reynolds number, Re is the Reynolds number, rho is the mass density, v is the velocity of flow, d is the diameter of the pipeline, mu is the viscosity of the fluid. Now first we are going to determine the shear stress distribution across the pipe. Right. Now we are going to determine the shear stress distribution and velocity distribution across the pipe. For this, consider a horizontal pipe of radius r. consider a horizontal pipe. Consider a horizontal pipe of radius capital R. Radius capital R. The viscous fluid is flowing from left to right. This is the left direction. This is the right direction. Left to right. Now, consider a fluid element of radius R. Consider a fluid element. Consider a fluid element of radius small r sliding in a cylindrical fluid element of radius dr. This is the cylindrical element. The radius is dr. Right? Consider a fluid element of radius r and sliding in a cylindrical fluid element of radius dr. And also the length of the fluid element is taken as delta x. Delta x is the length of the fluid element. R is the fluid element radius. This is the cylindrical fluid element radius dr. This is the diameter of the pipeline radius. Right. Now, if P is the intensity of pressure, now this is the phase A, B, C, D. Right, this is also we are going to right. This is or this is dr. Okay. Now, the intensity of pressure, P is the intensity of pressure, where P is the intensity of pressure. Therefore, this is phase A, B, this is phase B, D, C, D. Phase A, B, phase C, D. The intensity of pressure over the phase A, B is equal to small p. The intensity of pressure phase DC is equal to phase DC is equal to intensity of pressure at phase AB, that is this one, plus differentiation of intensity of pressure over the phase AB divided by in the direction of x into length of the element, that is d delta x. Right, this is the pressure. This is the pressure over the phase DC. Right, here forces acting on the fluid element. This is the diagram. This is the diagram. Here, what are the forces acting on the fluid element? One is pressure force on AB, and another one is the pressure force on DC, and shear stress. Right, first one, pressure force on AB. Pressure force on AB is equal to force equal to stress into area. That means stress or intensity of pressure. What is the intensity of pressure or pressure over the face AB? That is equal to small p into what is the area? Area, this is the circular. This is equal to pi r square is the area. This is the pressure force on the face AB. Next one, second force, pressure force on face CD equal to, here also intensity of pressure. What is the intensity of pressure? P plus dP by dx into delta x. This is the intensity of pressure into area pi r square. Into area pi r square. Right. Shear force equal to shear stress into, this is the elementary strip, 2 pi r is the circumference, 2 pi r into delta x is the length. Here we have three forces. One is pressure force on AB, and pressure force on CD, and shear force. This is the shear force. In this case, there is no acceleration, the flow is steady, because the flow is laminar and the flow is viscous, there is no acceleration. Therefore, the sum of these forces will be equal to 0. That means the force on AB is equal to stress into pi r square minus force on CD is equal to P plus dP by dx into delta x into pi r square minus tau into 2 pi r into delta x is equal to 0. Right? This is equal to P into pi r square minus P into pi r square minus dou p by dou x minus into plus minus dou p by dou x delta x pi r square minus tau into 2 pi r delta x is equal to 0. Now this one gets cancelled. Therefore, minus dou p by dou x delta x pi r square is equal to, move that side, tau into 2 pi r delta x. Delta x cancel. This is equal to, and pi gets cancelled, r square cancel, minus dou p by dou x into r is equal to tau into 2, shear stress into 2. Therefore, shear stress is equal to minus of dou p divided by dou x into r by 2. This is the equation for the shear stress. Shear stress equal to minus dou p by dou x into r by 2. Right, this is the same formula we have derived here. Right, based on this equation we are going to discuss about the shear stress distribution across the section. Right, shear stress distribution across the section. What is happening? Shear stress is equal to tau is equal to minus dou p by dou x into r by 2. This we have derived. Here dp by dx is constant. dp by dx is constant across the section. Suppose this is the pipeline. Across the section, dp by dx, the pressure with respect to x is constant at any section. Right, dp by dx is constant across the section, and 2 is also constant. Therefore shear stress tau is directly proportional to r. Therefore the shear stress varies with respect to r, or the shear stress distribution across the section is linear. Right, this is the shear stress distribution. Please, all of you, this is the pipeline. The shear stress at middle. What is the formula for the shear stress? Tau is equal to minus dou p by dou x into r by 2. R increases, shear stress increases. R is equal to 0, shear stress is equal to 0. That means this is the r, this is r, r is equal to 0, this is equal to 0, shear stress is equal to 0. That means this is equal to 0, shear stress is equal to 0. R equal to maximum. That means R equal to capital R. In place of R, we are going to capital R. The shear stress is maximum. Okay, this is the shear stress distribution at the middle of the pipeline and center of the pipeline. The shear stress is 0. Gradually towards the boundary, the shear stress increases. This is the shear stress distribution across the pipe. Right? Okay, clear? Now we are going to discuss about velocity distribution across the pipe. Right here, to obtain the velocity distribution across the section, The value of shear stress tau is equal to, this is value we know. The value of shear stress tau is equal to mu into du by dy. Is substitute the above equation. Above equation means already we have derived shear stress tau is equal to minus dou p by dou x into r by 2, right? Substitute the above equation. Write the, here one more point we are going to discuss here. That means if y is equal to only one point, y is equal to, this is the pipeline, this is the strip, outer strip, this is the inner strip. Y is nothing but distance between the two layers. Already I have explained. This is the diagram, this is boundary, this is the velocity profile, this is one velocity, this is one layer, this is another layer. The velocity is u here, the velocity is u plus this velocity is du plus du. This is one layer velocity, this is another layer velocity. The distance between two layers is dy, right? Like that, the distance between two layers is y is equal to capital R, this is the capital R, minus this is small r, this is capital R, minus small r. Y is equal to capital R minus small r, that is equal to this is capital R minus this small r equal to this value dr. Okay, here in place of dy, we are going to take in place of dy is equal to minus dr. This is only the point we are discussed here, right? Clear? Right. Therefore, based on the boundary conditions, based on the given diagram, y is equal to minus dr. Therefore, this equation can be tau is equal to mu into du by dr. In place of dy, we have taken minus dr. This is equation number 2. Already we have derived equation number 1, that is shear stress tau is equal to minus of dou p by dou x into r by 2. This is the equation number 1. Now this is tau is equal to, this is the value, and tau is equal to, this is the value. These two are equal. These two are equal. Therefore minus mu dou u by dou r is equal to minus dou p by dou x into r by 2. This equation already we have derived. This is the shear stress is equal to minus mu into du by dy. In place of dy, we have taken minus dr. Therefore, these two equations are, the equation 1 and equation 2 are equal, right? Du by dr is equal to dp by dx into 1 by 2r into mu. This is from this equation. This equation integrate with respect to r. Du is equal to integral dp by dx into 1 by 2r into r dr. Right here, dou p by dou x into 1 by 2r taken out, integral r dr. Right, this is equal to right, this is equal to dou p by dou x into 1 by 2r. Here this r is integrate with respect to r, that is equal to r square by 2 plus c. C is the constant of integration, right? This constant of integration is determined based on the boundary conditions, right? U is equal to dp by dx into 1 by 4 mu into r square plus constant of integration, right? Now we are going to determine the constant of integration based on the boundary conditions. U equal to dou p by dou x. I have used dou p by dou x or dv by dx. Don't confuse, please. Right? Right. Here u equal to dou p by dou x into 1 by 4 mu r square plus c. This is already we have derived in the earlier slide. We want to determine the constant of integration. Right? As per the boundary conditions r equal to small r equal to capital R, u is equal to 0. Suppose this is the pipeline, this is the center line, this is the center line. Okay, this is the radius r, this is the radius r, right? R equal to capital R equal to capital R, velocity at this point, at this boundary, velocity at the boundary is equal to 0. Small r equal to capital R, that means small r equal to capital R, automatically the velocity at the boundary is equal to 0. Therefore, substitute these values here. U is equal to 0, dou p by dou x into 1 by 4 mu into r square plus c. So, in place of small r equal to capital R, we are going to substitute here, this is capital R square. Therefore, C equal to, from this equation, C equal to minus of dou p by dou x into 1 by 4 mu into r square. Right? This value is substitute in the above equation, because here only unknown is C. Unknown is C. C is determined here. C is equal to minus dou p by dou x into 1 by 4 mu into r square. This value is substitute here. Therefore, U is equal to dou p by dou x into 1 by 4 mu into r square. This is the value. In place of C, we are going to take in this value, that is equal to minus dou p by dou x into 1 by 4 mu into r square. Here we are going to take the constant dou p by dou x and 1 by 4 mu, then r square minus small r square, right? In this equation, u is equal to, this is the equation, dou p by dou x into 1 by 4 mu into r square minus, that means capital R square minus small r square. Here, dou p by dou x is constant across the section. Mu equal to viscosity of the fluid is also constant, and radius of the pipe is also constant. Only variable is the small r, that is the radius of the fluid element. Right? The velocity u varies with respect to square root of r. Square root of r. Based on this equation, velocity is directly proportional to the r square. Therefore, the equation is parabola. Therefore, the equation is parabola. This is the equation. In this equation, all parameters are constants across the section, and only r is the variable. Therefore, velocity is directly proportional to r square. Therefore, the equation of velocity distribution is parabola. Right? This is the velocity distribution diagram. The center line of the pipeline. This is the velocity distribution in case of viscous fluids flowing through the pipe. Where the velocity is maximum in case of pipe flows? At the middle, at the center line of the pipe, the velocity is maximum. Therefore, r is equal to 0. Radius is equal to 0. This is a pipeline. This is the radius. This is one strip. This is small r. This is capital R. Capital R. Small r is equal to 0. Radius is equal to 0. Automatically, velocity is equal to 0. Velocity is equal to maximum. Radius is equal to 0. Velocity is equal to maximum. Right? Already I have explained velocity distribution in case of circular pipe flowing the viscous fluid. Viscous fluid flowing through the circular pipe, the velocity distribution already I have explained. Based on that, r is equal to 0, u is equal to maximum. Therefore, in place of r, we are going to take 0. R is equal to 0. This equation can be mu. U maximum, the maximum velocity is equal to minus dou p by dou x into 1 by 4 mu into r square. This is 0. Right? Then finally, the maximum velocity, viscous fluid flowing through the pipeline, the maximum velocity equal to minus 1 by 4 mu into dou p by dou x into r square. Right? This is about the maximum velocity. Then we are going to determine the average velocity in the pipeline. Right. The average velocity is obtained. The average velocity is obtained by dividing the discharge of the fluid across the section by the area of the pipe. The average velocity is obtained, the discharge of the fluid across the section divided by area of the pipeline. Now, we are going to take the discharge q across the section is obtained by considering a flow through a circular ring. Right, for this purpose the discharge q across the section is obtained. The discharge q across the section is obtained by considering the flow through a circular ring of radius of elementary radius small r and the thickness is dr. Right here, this the radius of the elementary strip is smaller and thickness is dr. Thickness is dr. Right. Now we are going to take a fluid flowing per second through this elementary strip is equal to fluid flowing through the elementary strip is equal to what is the formula? Like discharge equal to velocity into area. Right here, velocity at a radius r into area of the ring element. What is the velocity? Already I have derived. Velocity is equal to minus dou p by dou x into 1 by 4 mu into r capital R square minus small r square into area of the ring or 2 pi r into dr. This is the velocity into area. We have the flowing liquid from the pipe. Okay, dq, that is over the small strip. The discharge over the small strip or small element equal to area of the strip into velocity of flow over the strip. Right, velocity of flow over the strip already we have derived and area of this strip of ring is equal to this one. Right, velocity already we have determined of radius r, that is minus 1 by 4 mu into dou p by dou x bracket begin capital R square minus small r square. This is the velocity. This is the velocity into area 2 pi r. This is the strip. This is small r is the area, that radius of the elementary strip. This is the cylinder radius dr. Right, the 2 pi r into dr. First integrate this equation with respect to r and limits 0 to r. This equation integrate with respect to r and the limits equal to 0 to r. Now integral 0 to r dq is equal to integral minus 1 by 4 mu into dou p by dou x into r square minus small r square into 2 pi r dr and the limits equal to 0 to r. This equation integrating with respect to r and limits 0 to r. Now this is equal to this is constant value, this is also constant. Right, this is also constant. Now taken out minus 1 by 4 mu dou p by dou x into this and also 2 pi then r into capital R square small r minus small r cube dr. This is the integral 0 to r. So all constants are taken out. Integral 0 to r square small r minus small r cube dr. Now this is integrate with respect to r. This value, this is equal to again minus 1 by 4 mu into dou p by dou x into 2 pi. This is equal to r square. This is equal to r square by 2 minus r power 4 by 4 0 to r. Now we are going to apply the limits 0 to r. Then we have this is equal to this is equal to minus 1 by 4 mu into dou p by dou x into 2 pi 0 to r. In place of r square we are going to substitute capital r power 4, r power 4 divided by 2 minus r power 4 divided by 4. Then we have this is equal to minus 2 pi by 4, 2 ones 2 twos, this is equal to minus pi by 8 mu dou p by dou x into r power 4. Right, this is the discharge q. Discharge q is equal to minus pi by 8 mu dou p by dou x into r power 4. This is the discharge derived here. Now average velocity is equal to discharge flowing through the entire pipeline divided by area of the right. Now dq is the discharge over the strip. Discharge equal to velocity into area. Here velocity at radius r into area of the ring element. Right, what is the velocity? Velocity already we have derived, that is equal to velocity is equal to minus 1 by 4 mu dou p by dou x into r square by small r square. This is the velocity into 2 pi r into dr is this is the radius r, this is the dr. Right, now this equation integrate with respect to r and also take the limits 0 to r. Therefore integral dq is equal to integral 0 to r minus 1 by 4 mu dou p by dou x r square minus small r square into 2 pi r dr, and also limits this one. Now this is equal to q is equal to minus 1 by 4 mu dou p by dou x into 2 pi taken out. This is equal to only r square into r into r square into r square is nothing but r cube dr. This is the integral 0 to r. Right, from this one integrate with respect to r, this is equal to minus 1 by 4 mu into dou p by dou x into 2 pi. Integrate with respect to r, this is r square by 2 minus r power 4 by 4 0 to r. This is equal to, substitute the r value here. Finally we have minus 1 by 4 mu into dou p by dou x into 2 pi. Substitute the value here, this is equal to r power in place of small r square, r substitute here, r power 4 by 2 minus r power 4 by 4. Right, this is equal to minus 1 by 4 mu into dou p by dou x into 2 pi. This is equal to r power 4 by 4. 2 gets cancelled. This is equal to q is equal to minus 1 by 4 mu into dou p by dou x. This is pi by into r power 4 by 2, 8. Therefore q is equal to pi by 8 mu into dou p by dou x r power 4. Right, now average velocity is equal to q by area. Average velocity is equal to q by area. What is q? Q is equal to minus pi divided by 8 mu into dou p by dou x into r power 4 divided by area is equal to pi r square. Area equal to pi r square. This is equal to pi by 8 mu into dou p by dou x into r power 4 into 1 by pi r square. Pi gets cancelled, r square, this is square, minus, this is equal to minus of 1 by 8 mu into dou p by dou x into r square. This is the average velocity. Minus 1 by 8 mu into dou p by dou x into r square. Right? This is the average velocity. Average velocity is equal to minus 1 by 8 dou p by dou x into r square. This is the average velocity. Finally, we want to develop the relation between the average velocity to maximum velocity or maximum velocity to average. Finally, we are going to determine the relation between the maximum velocity to average velocity. Average velocity, this is the average velocity. Now, u maximum to u average is equal to, what is the maximum velocity? Already we have determined maximum velocity equal to 1 by 4 mu dou p by dou x into r square. This is the maximum velocity. What is the average velocity? This is we have determined here. That is equal to minus 1 by 8 mu into dou p by dou x into r square. Right here, minus cancel. Dou p by dou x cancel. R square cancel. This is equal to mu is also cancelled. That is equal to 1 by 4 divided by 1 by 8. That is equal to 1 by 4 into 8 by 1. 4 1, so 4 2. So this is equal to 2. In case of pipe flow, viscous fluid flowing through the pipe, the ratio of maximum velocity to average velocity is 2. Right? This is about relation between the maximum velocity and average velocity. Now, this is the last point. Drop of pressure for a given length of the pipe. Suppose this is one pipeline. At section 1 pressure is P1. At section 2 pressure is P2. The distance between the section 1 and section 2 is L. One boundary, the distance from the boundary, this section 1 is x1 distance, and from this boundary section 2 is x2 distance. This is about diagram. Now, average velocity already we determined. Average velocity equal to minus 1 by 8 mu dou p by dou x into r square. This is the average velocity. Right? From this equation, minus dou p by dou x is equal to 8 mu u average divided by r square. Now, integrate with respect to x and limit so 2 to 1. Already we have derived average velocity. From this average velocity, dou p by dou x is equal to, this is the equation. Right? This equation, integrate with respect to x and also take the limit so 2 to 1. Right? This is integral minus dou p, that is limits 2 to 1, is equal to integral 2 to 1 8 mu u average divided by r square. Right? This is the integrate with respect to x dx, so that all are the constants here. Therefore, dou p is nothing but change in pressure is nothing but minus P1, that is the pressure at section 1. The pressure is more here. The pressure is less here, because the pressure at this phase already we have determined the pressure is, intensity of pressure is small p here. At this point, suppose this is A, this is B, this is C, this is D. The intensity of pressure over the phase AB is equal to small p. The intensity of pressure over the face CD is equal to pressure small p plus dou p by dou x into distance. So that the pressure at section 1 is more P1 minus P2. P1 minus P2 is equal to constant 8 mu u average divided by all our constants. So this is x1 minus x2. This is the equation. Now this is minus P1 minus P2. That means pressure at section 1 minus pressure at section 2 is equal to minus is taken out. Minus is taken out. 8 mu average velocity divided by r square. This is x2 minus x1. x2 minus x1. This x2 minus x1 is nothing but this is x1, this is x2. x2 minus x1 is L. x2, this is the x2 minus this is x1, this is x1. x2 minus x1 is equal to this is the length L. So that we are going to substitute in place of x2 minus x1, substitute L. Therefore minus gets cancelled. Therefore P1 minus P2 is equal to 8 mu u average velocity divided by r square into L. This is the equation we developed. P1 minus P2 is known as drop of pressure, that is from section 1 to section 2. Right here P1 minus P2 is the P1 minus P2 is equal to 8 mu average velocity divided by r square into L. Right. P1 minus P2 is known as pressure drop, that is from section 1 to section 2. Section 1 to section 2 pressure drop. P1 minus P2 is the pressure drop. And this equation divide both sides by rho g. Therefore P1 minus P2 divided by rho g is equal to 8 mu u average divided by r square into rho g. Right? P1 minus P2 divided by rho g is known as loss of head. Pressure divided, already I told you, P divided by rho g is nothing but pressure head. In this case, P1 minus P2 divided by rho g is nothing but loss of head. Therefore, loss of head is equal to 8 mu v average velocity divided by rho g into r square into L. This is the loss of head. The liquid is flowing from viscous flow from section 1 to section 2 to section 1 to section 2. The loss of head is equal to 8 mu u average L divided by rho g r square. Right here in this case r square is nothing but what? This is equal to d square by d by 2, d square by 4. This is moved top side. This is equal to, right, loss of head is equal to 8 mu u average into L divided by r square rho g. In place of r square we are going to take d by 2, that is d square by 2 square. This is equal to 32 mu u average into L divided by rho g d square. This is the formula for the determination of the loss of head if the liquid is flowing from section 1 to section 2. This equation is also known as hygiene Poiseuille's formula. Right, this is about if the viscous fluids flowing through the pipe, velocity distribution across the section, shear stress across the section, and the ratio between the maximum velocity to average velocity, and also finally we have derived the drop of pressure and loss of head if the water flowing from one section to another section. Right, thank you one and all.